Thank you, Katie. It's a real pleasure to be part of this. I'm very new to quantum. So quantum is what I know very little about. But I'm excited to tell you today a little bit about some new optimal transports. So this is something that I was working on together with 4 other professors in Germany, which you may know. So Martin Berger, Matthias Erbar, Daniel Mattes, and André Schlichting. And even though this has been published earlier this year, actually the first version of this was already on arXiv more than 2 years ago. So in that sense, it's not that new anymore. But there's still some really interesting open questions that I'm hoping to pose to this audience that we still have not been able to figure out, even after 2 or 3 years. That actually we started working on this in 2020. So I should say 5 years that we have been thinking about this. So with this audience, I guess the Wasserstein metric needs no further introduction. But just as a starting point, I put here different formulation. Like if we know that there is a transport map, then we can think of the Wasserstein 2 metric as pushing forward mu0 to mu1. Then there's the Kantorowicz formulation, or the static formulation, and then there's also dynamic formulation. And it's very nice to have had Katie's talk earlier, because that was already a nice way of thinking about the static versus the dynamic formulation. So for the rest of this talk, I will be focusing on the dynamic formulation. And I will be looking at a generalization, in some sense, of the way that the dynamic formulation is posed here. And I think instead of trying to give you a long trailer, I would just jump straight in and tell you what is the covariance-modulated optimal transport metric, and then I will tell you what we know about it. So that's it. That's the covariance-modulated optimal transport distance. So you see it's also dynamic formulation. We're minimizing a kinetic energy along paths. And these paths, they satisfy also a continuity equation with some velocity field, vt. So this is exactly the same setup as Wasserstein 2. Should look very familiar. The only difference is the way that we measure the size of the velocities. So in the classical Wasserstein 2, I can maybe go back on the slide before, we just have the normal Euclidean norm squared, right? So really the only thing that changes is the way how we measure the size of the velocities. And what we use instead is this definition. So we have an inner product between 2 vectors, but the inner product is weighted by the inverse of the C. And the C is the covariance matrix of mu. So in this sense, it's actually quite intricate, because the notion of inner product that we put on the velocities itself changes as you move along the path, right? Because this here is mu t, so it changes as we move along the path. And what happens is that actually this metric then behaves quite differently in some ways, from what you're used to with the Wasserstein 2 metric. For one, there's a competition effect that shows up. For this, maybe just to draw a little picture. So let's say that I have my mu0 here, and I have my mu1, and then I transport in between, right? So in the middle, I have some mu t, and let's say that this mu t somehow looks like that. I don't know. And now I ask, what is the covariance matrix of this mu t? And you observe that maybe in this direction, you have a very large spread, and then in this other direction, you have a very small spread. So because I'm taking the inverse here, right, it means that if I try to push mass in directions where the covariance matrix is very spread, so it has a large eigenvalue, then the cost is cheaper. So it's not anymore true that necessarily the cheapest way of transporting mass is just a straight line. It might actually be cheaper to spread out the mass a little bit in these directions where the covariance matrix is large in order to reduce the overall cost. And so you have sort of this competition effect between minimizing the path lengths that each of the mass particles have to travel and spreading the mass out. Now, why do we why are we interested in this? Why do we even want to put a matrix here? I hope I can show you later on why that is the case. But basically, we came to this through gradient flows in this metric. And it turns out that actually the convergence properties in this matrix are very nice. And you get acceleration effects in some cases. OK, so here's sort of the wish list of what we would like to be able to do with this metric. So we want to understand really the geometry and show existence of geodesics. We had earlier in the discussion in Katie's talk, I think the comment that, oh, but geodesics is one thing that, of course, should exist and is easy to show. Well, it's definitely not easy in this case. And actually, we're still not able to show it in general. So there's still an open question there today. And then I will also relate this covariance-modulated metric to a variance-modulated metric, which is actually related to a paper by Eric and Wilfried from 22 years ago. I will get to that later. And then we would like to understand the convergence properties of the corresponding gradient flow structure and how that's related to convexity properties of the functionals. And before I get to this, I just want to tell you sort of the trailer of why this is cool. So if I take the KL divergence, or the relative entropy, in the classical Wasserstein 2 metric, and I look at the gradient descent, then, oh, that's exactly what I didn't want to happen. If you know that, let's say, your target, so this is the relative entropy, right? If my target is just a Gaussian, this B is just some fixed covariance matrix of the Gaussian, then I can look at the lower bound on the spectrum of the inverse of B, and that will give me the rate of convergence, right? Here, if I look at the gradient flow in this covariance-modulated metric, for the same choice of energy, we're getting a rate 1. I mean, there's a 2 here, but then when you relate it to the Wasserstein metric, you would get rate 1. So that's the magic. Basically, for where you use the classical Wasserstein 2, you will get a rate that is determined by the lower bound of the Hessian of your target. Now, you get a rate that is independent of your target. And this is very useful for sampling algorithms, for instance. I mean, there's probably many applications from this, but in sampling, you're trying to sample from some target measure that is complicated to sample from. And so instead, you sample from something that is easy, and then you set up sort of a system, like an evolution of the particles, so that you derive approximate samples from the target that you actually want to sample from. And for this to be effective, you want this to happen fast. So the rate of convergence, if you then look at the sort of distribution of the particles, the rate of convergence at which this happens sort of tells you how useful it is in practice or how achievable it is in practice. So this is really a big difference. So this is how we got interested in this. And we wondered, like, why does this happen? So if you just change this inner product, right, and you put the matrix there, why do you suddenly get a rate 1? And there's something that we observed. So here I'm comparing the Wasserstein 2 metric with a metric that's not our covariance-modulated metric, but it's a related sort of constrained version of this covariance-modulated metric that I will introduce in detail in a few slides. So don't worry, we'll get to this. But what I want you to remember is this. So if I take, again, the KL divergence, but I split it up into just the entropy plus the potential term. So here, again, I'm taking just a target that is Gaussian. Then in the classical Wasserstein 2, we know that the entropy is convex, but not strictly convex, right? And if your potential here is just quadratic, right here, this is, again, the weight, which is like B inverse in the inner product, then that will give you convexity, strict convexity of your potential part. And that's what gives you the rate. That's why you have like this rate of convergence. Now, if I look at convexity of the same functionals in this new metric, then the entropy is strictly convex with rate 1, and the potential is just the second derivative is equal to 0. So basically, you're getting rate 1 because the convexity properties of the same functional in this new geometry have changed. And so this is a problem that I discussed with Lorenz already some time ago, which I think is a very interesting problem, is sort of how can we explain this, right? Like, is there maybe some curvature of the underlying space? The fact that we're now putting a different metric on this space, is there some curvature properties of the underlying space that cause this change in convexity property of the functionals? I'll just leave that out there as an open question. But yeah, I will get back to what this metric is. But before, let me just tell you how we even came up with this metric. And actually, we got to this through inverse problems. So my background is in PDE analysis. And then I did a postdoc at Caltech, and I started working with Andrew Stewart. And there I started learning about Bayesian inverse problems and sampling as a way of solving Bayesian inverse problems. And this is how we ended up proposing this metric. So let me take you on a little journey into inverse problems. It will just be a few slides. So here I'm considering a very general inverse problem, so the x is some parameters that we want to find. The g is a forward map that takes parameters to observables. And then this space Rk is where the observables live, so the y is some measurements. And we're here assuming that we have noisy measurements, so there's plus this eta, so this eta is some noise. And we assume that we know what this noise distribution is, let's say. I mean, as a sort of thing for you maybe to have in your mind is that when you have like weather forecast, you may have many coupled PDEs that predict your weather or your climates. And what you maybe need to input is some initial condition or some boundary condition or some diffusion coefficient. And if you have that, then you can run a numerical solver and it can give you a solution. And so that would be the x. It would be like your diffusion coefficient, some constant that goes into the PDE. And then maybe you take some time averages with the g on top of numerically solving the PDEs. And then the y is what you actually go and measure, and that's what you then compare. OK, so you can write down like a prior belief on what these parameters x are. So let's say we assume that's Gaussian. Then you can write down a likelihood given by this relationship between your parameters and your measurements. And then you apply Bayes' theorem, and you get your posterior measure, which I will write down as e to the minus f, where f is this function. So you see that here this quadratic term comes from your prior, and this term comes from your likelihoods. And then typically what you want to do, for instance, in parameter estimation is that you want to maximize this posterior. You want to find the parameter that most likely gave rise to the data that you observed. Or you may want to do uncertainty quantification, in which case you want to sample from this pi and get an idea really of the distribution of these parameters given the data that you observe. So you want to do either optimization or sampling. Now, here this g, you have to think of it as really a very complicated black box type function. So you can stick in an x and it spits you out a value y, but you don't really have an idea of what this g looks like. It may not even be differentiable. So basically you want derivative-free algorithms that allow you to do optimization and sampling. And there's a very famous family of algorithms that does that, also the filtering, called ensemble Kalman methods. And this is one of the, Andrew is one of the world experts on this. But in 2020, we proposed a new algorithm in this family called the ensemble Kalman sampler. And so it's basically an interacting particle system. And it's doing what I mentioned before. So basically, you sample from something that's easy to sample from, and then you evolve your particle system in a way that after a long time, you sample from, or you have approximate samples from your target distribution. So this is what this algorithm is proposing to do. And this first term here is something that's very common in all of the ensemble Kalman methods in this family. And you see that here you're trying to drive particles together to collapse, because this is the mean of G. And then here you're trying to drive particles to match the data. And then this is a term that comes from the prior. And this is a term that adds noise so that you don't actually fully collapse, but you actually retain sort of the shape of your target that you're trying, from which you're trying to sample. And so the important point is the covariance matrix here. And the reason, really the reason why we proposed the particle dynamics in this way is to be able to still have a gradient flow structure in it, to then be able to do analysis. Because actually a lot of these algorithms, they're quite popular in the sense that when you have high dimensional problems where MCMC is not really feasible, then this is one of the few things that you can actually do. But there's very few theoretical proofs to actually guarantee that what you're sampling from or where you're, even in terms of like the measures, the laws of these particles, where they're converging and how fast and so on. So we were hoping that by setting it up in a way that you have a gradient flow structure that you actually can prove some things. And so here's how the gradient flow structure pops out. So let's say you linearize this forward map, and then you take a mean field limit. So you take the number of particles to infinity. Then sort of a mean field particle evolves according to this equation. And I could do the computation for you sort of in a few minutes to see how out of this like sort of difference approximation you have this preconditioned gradient pop out. That you can really do that explicitly. But that's really nice to see that really what you get is a preconditioned gradient descent. And then if you ask, okay, what is the PDE that the law of this random process follows, you get this PDE here. And in this case, really, this is a gradient descent with respect to this covariance-modulated optimal transport. And you see that it looks exactly the same as if you would do gradient descent with respect to the Wasserstein 2 metric of the same functional, except that now you have this covariance matrix here. So basically, by changing the metric this way, by putting this inverse of the covariance and then a product, what you get is this covariance matrix in front of the gradient when you look at the gradient descent, or the gradient flow. And you can already see this by just simply differentiating the energy along solutions of this PDE. And then what you get is this guy, which I will call a Fisher information, like minus some Fisher information. And you see already the structure here that I was talking about before, that you think of these as velocities, and then you have the inner product weighted with the covariance matrix. Now, this is not exactly what I wrote down before. Let me go to the next slide to show you. So what I wrote down before was this, right? Conditioned on a PDE without a covariance matrix here. But these are actually the same thing. So it's a little bit the same thing that Katie explained this morning by putting the QIJs, the weights, into the equation versus putting it into the minimization problem. So here here you have the covariance matrix in your equation, and here now I have it in your minimization problem, and that allows you to see really the effect, what I was saying in terms of spreading the mass, that it has on which velocities or which directions are preferred. And what you see from this also immediately is that basically you cannot send any mass in the directions that are in the kernel of this covariance matrix. So if you have like a degenerate covariance, right, then it could well happen that you have two measures that have distance infinity, right? Like let's say if I have two measures that are supported on different subspaces, then there's no way I can transport mass from one to the other. Right, that's what I kind of said here. Right, that the support remains constrained. So what about the convergence rate? So there's a very interesting property of this metric that we saw, which is this splitting in shape and moments. So basically, instead of writing one minimization problem, you can write one problem where you just look at the difference in shape, so the profiles, and then plus another minimization problem where you just look in the difference of the moments. And they don't completely decouple. They decouple up to rotations. And it took us about a year to realize that. So we had this really nice splitting, and then we were able to prove lots of nice things. But then there was always something that wasn't quite adding up, and it was the fact that we missed this degree of freedom. And once we realized that actually it's up to rotations, then a lot of things started making sense. So this is kind of an informal statement. So we take the mean and the covariance of our source measure and the mean and covariance of the target measure, and then we look at the distance just between those. And then we also normalize our measures. So these mu0 bar and mu1 bar is basically mean zero covariance identity. So you normalize your measures. And this is where the rotation comes in. I will explain this more in a minute. So you rotate one of them. And then, so you take a distance in shape, and then you minimize over all the rotations. And because you have the splitting, that gives you a very nice structure to prove things. OK, so where does this degree of freedom come from? So I want to talk about the normalization. Let me talk about this one first. So how do I normalize my measure? So let's say I have some mu, and I want to normalize it so that it has mean zero and covariance identity. Well, I just push it forward with a transport map like this, where I require that the AAT is equal to C. So basically, the A has to be a square root of C. But it doesn't necessarily have to be symmetric. Like it could be, so here we're taking any left square root, and for any left square root, this is true. And this is exactly where the degree of freedom comes from, because I can parameterize all the possible left square roots with this orthogonal matrix Q, and that will later lead to this like degree of freedom in the rotations. So when I write C to the half, I mean the choice of square root that's symmetric. OK, so this is how the splitting pops out. So I start with my covariance-modulated metric, the way that I wrote it down, and I just rewrite it in a funny way. So what I do is I take curves, vectors. So these are like, can think of a mean, but it's prescribed. It's a fixed curve. It's a fixed matrix curve. And then I say, OK, I want to now minimize the same thing as before, but constrained on the fact that the mean is always MT and the covariance is always CT. So this is now a constraint minimization problem. And after I compute that, I then take the minimum over all such curves, and then I get the same thing, right? But now, after I wrote down this problem, I can normalize. And then you see that the PDE becomes a PDE for the normalized curve. And you see that the action functional that we're minimizing splits exactly in two terms, where one term is basically the action functional for the normalized problem, and the other one is something that only depends on the mean and the covariance. And that's basically where the splitting comes from. OK, and there is a condition you will see pop up later, which is that the choice of this left square root that we take, we want the A minus 1 A dot to be symmetric. And the reason for that is because then we can get all the same nice properties that you would expect from Wasserstein 2 with a Kantorovich potential so that the V is a gradient, thanks to this property. Because we have a lot of choices, we can as well make this choice for the left square roots. And this allows us to now define this metric that you saw earlier in my statement about convexity. So it's basically just a constraint metric where I want the mean and the covariance to be zero in identity all along the path. Yeah, any questions? Yeah?
Sorry, go back. So can you say where the mu naught hat and mu 1 hat come into this definition?
Oh, I think there's a typo. There's a typo.
Thank you.
Thank you. Yes, so there should be a hat here and a hat here. Yes. So all it's saying is that you take any measure, you normalize them. After you normalize them, they have zero mean covariance identity, and then you can compute yes. So you can only enter this constraint metric, you have to stick something in that's already normalized. Well spotted. Okay, so we can make our choice of left square roots by solving a matrix ODE. So let's say I have my path of covariance matrix given, and then given that path, I started at the symmetric square root, and then I evolve this equation. That has a unique solution, fine. And then it satisfies this property that I want, and that I will use that to normalize. And then you can sort of look at this object here. The only reason why I define that is because this is where we get the rotation coming in later. So you can see that actually if you look at C minus a half times this A, that you get then a rotation matrix. And this is exactly the degree of freedom. So in here I have a choice because I can, of course, I can choose the initial condition or the final condition. But here I fix my initial condition, and then on top of that, later on I will constrain what the final rotation matrix should be at t equal to 1. And that sort of subselects possible choices of curves CT that I'm allowed to stick in. If I constrain that at the end, at t equal to 1, they end up at a particular matrix. And that's exactly what happens here. So this is the terms that came out of the splitting, what I showed earlier. I just defined that to be a functional, and then I constrain the possible curves for the covariance matrix to be those that match a specific given R. And then the unconstrained moment optimization problem would just be if I minimize over all choices of R. Okay, so this is now the rigorous statement of the splitting without the informal in the title. So I just repeat the metric up here. When I put T bar, it just means that I'm normalizing with the symmetric square roots. And so by normalizing with the symmetric square root instead of the AT that solves the little matrix ODE, that's where I get the rotation show up here. And so this is exactly the statement that we had before, just that now you know what the moment part is and you know what the constraint part is. So here you get the shapes and the moments. And then if one of your source or target measure is actually spherically symmetric after normalization, then you don't have up to rotations. You get a full splitting. Yes?
Sorry if you already explained this. What's meant by P2 plus, and what is suitable mu0, mu1 in P2 plus?
Oh, yeah. So here we're restricting to the measures that actually have finite distance, this covariant modulated distance. Because as I was saying, if you start with two measures that have like covariance matrices with different support, then the distance would be infinity. So I'm just looking at those measures that have finite metric.
So the equality is when both are finite?
Yes. I mean, okay, if you have infinity, maybe you could argue that one of these is also infinity, and then you're still fine. But yeah. Okay. By the way, I don't have a... Oh, I can look at this clock. Great. Okay, I want to briefly mention something about variance-modulated optimal transport, because this relates to the work by Eric and Wilfried that I mentioned. So you can do the exact same thing by putting a variance there instead of a covariance. So instead of putting a matrix, you put a scalar. So here's the metric that you get. Call it variance-modulated optimal transport. So you have 1 over variance instead of c to the minus 1, right? And since it's a scalar, you can pull it out. And then you can do exactly the same argument. You get a splitting. Now, because it's all scalars, there's no rotations involved. It's an exact splitting. And then you get just the difference in moments, which is given by this very nice expression. And you get this constrained variance matrix, which is basically saying, I'm just minimizing the usual kinetic energy subject to the same PDE, but now I'm constraining the mean and I'm constraining the variance. And this metric actually is what Eric and Wilfried looked at. And what they observed, which was really nice, is that how do you prove that geodesics exists for this metric? So what they observed is that you can look at your Wasserstein 2 geodesics which we all already know exist. We know how they behave. You take them and you normalize them. So now they have mean 0 and they have variance 1. And then they turn out to be geodesics for this. So this gives you the proof of existence of geodesics for this variance-modulated metric. And we were thinking, OK, great, let's do the same thing for the covariance-modulated case. And it didn't work. And for a long time, we were thinking, OK, this has to work. Like, we're just not figuring out what's the right way of proving this. But I can show you. Do I have it on the next slide? Yeah, I will get there in a second. Oh, how do I get back? I get back here. Yeah, it's not the case for our covariance modulated. And this is explicitly solvable. So you can write down, in time, what are the geodesics for the mean and the variance. OK, so what about existence of geodesics for our covariance modulated case? So for the moment part, everything is fine. So we can show existence of geodesics. We can write them down. We can write some we can find some nice properties about them. So that part is OK. But then for the constraint part, for the shape part, essentially, that's where we don't know. So here's a picture. Andre made these on New Year's Eve, so he chose stars because he was in fireworks mode. So here we have a source measure, which is a Dirac. And the size here tells you the mass at that Dirac. And then your target is these two stars. And again, the size tells you the... And then, so in blue, you see the optimal transport when you take the Wasserstein 2 geodesics and then you normalize. And then the red one is what you get when you just solve the covariance modulated. Now the constraint, the covariance constraint one directly. And they don't quite match, right? And if I look at a different example, I mean, we run tons of examples, but here you see that even the plans are different. Like in this case, the one where I normalized the Wasserstein 2 geodesics is getting sent here, whereas if I look at the covariance constraint one, it's getting sent here. So there is a subtle difference. Something is happening, right? So, OK, we need to show existence of geodesics. And this is what we have. So we basically have two partial results. And the general question is still open. So the first partial result is that if we assume that we have at small distances, then we get existence of geodesics. The other result is if we assume some symmetry. OK, so let me first say something about the small distance results. So here, the problem, why we're not able to do it in general, is that when you try to show existence of geodesics, normally look at minimizers of your minimization problem. And now we have constraints. So basically, you want to show that the minimizing sequence preserves the constraints in the limits. And for the mean, that's OK. But for the covariance, that's not necessarily true. So if I know that I have a sequence rho epsilon that has covariance identity for all epsilon, it doesn't necessarily mean that the limit still has covariance identity. And that's basically what makes this difficult. So what we need, in addition, is some tightness of the second moments. And we were only able to show this with some control on the distance. And this really comes from the way how we did the proof, because we did a proof by contradiction. And yeah, if any of you has any idea how to do it differently, or how to get rid of these assumptions, then I would be very happy to hear about it. So the second proof we obtained by looking at the dual formulation. And if you look at the dual formulation, then it looks like this. So the constraint shows up through this lambda t. And here we assumed some symmetry. So we assumed some default reflection symmetry, which basically looks like that. So you say that your measure is symmetric by reflection above all coordinate axes. And if you assume that, then you get existence of geodesics. And the reason why we're not able to prove it in general is so we get, for the general case without symmetry, we get a matrix ODE involving this guy, which we don't know how to solve. It's very frustrating because it's just a matrix ODE. We put it on stack exchange, and so on. Again, I'm happy to show it to you, and if anybody has any ideas, I would be very happy to hear. So that's where we are at with the geodesics. Now, convergence properties. That's sort of the whole point of why we're interested in this. Let me go again to the Gaussian case. There's something really nice that happens if your target is Gaussian. So here again, let's look at the KL divergence. Then we can write down explicitly the gradient flow, where the target shows up here with the B inverse. And now, if we take the solution of this PDE and we normalize it, and here we choose our specific choice of AT, which solves this ODE, which gives us the nice structure, we end up with the Ornstein-Uhlenbeck process. So basically, then this just solves like the vanilla Fokker-Planck, which is super nice. And that actually allows us to show also some splitting results for the KL divergence and for the Fisher information. So in a similar way, like you see the splitting in the definition of the metric, you can write your relative entropy as a shape part. So the shape basically says, okay, if I normalize my target, now I just get a standard Gaussian, and I normalize my raw, and I compare these. So this is the difference in shape. And then I compute what is my mean and my covariance of my raw, and I look at the Gaussian with that mean and covariance, and I compare it to the target. And you know that for KL, you have a very nice expression for this, right? Like some explicit equation. And then similar, you also get a splitting in for the Fisher information. Right, and then we get the advertised decay, where you see that here you have a lambda now. So instead of having a rate with up here in the exponential, you instead get a multiplicative constant, where that constant, okay, I wrote out here what it is. It's a bit long, but you can think of this as kind of a condition number, because what this is doing is it's comparing the initial covariance with the covariance of the target. But the point is that the rate is independent of the targets. And so here's a little comparison between the covariance-modulated and the variance-modulated story. So I wrote down the gradient flows in both cases. We're choosing the same KL divergence, again with the Gaussian target. And you know, you see that what I just said for the covariance-modulated case, that you get this multiplicative constant in rate 1. But then if you do variance-modulated optimal transport, you still get the dependence on the target up in the rates. So what that tells you is it's really important that this thing is a matrix that you put there and not a scalar. Because what it's doing is kind of dynamically adjusting the spread in different directions differently in order to sort of counteract. I mean, it's already taking into account the knowledge that you gain about the Hessian of your target dynamically as the covariance matrix approaches, and that kind of gives you this asymptotic speed up. And this is, again, some sort of relative condition number. Okay, so maybe I went faster than what I thought. No, I'm on time. I'm supposed to be. Perfect. Okay, so then let me just sort of wrap up. I know there are some parts that I maybe went a bit quick. I'm happy to sort of dive a bit more into the details of the story with the rotations. But just a sort of takeaway, so we got to this from trying to solve Bayesian inverse problems, and our goal was to propose an algorithm that uses this idea of the ensemble Kalman methods, but in a way that we can actually prove something. And the way to prove something for us, we were thinking, okay, let's try to do it so that we get a gradient flow structure, and then we can use that in order to get rates of convergence. I have to say, though, the only proofs we have up to now for the convergence are for Gaussian targets. And that is very frustrating, because even though the gradient flow structure is very nice and it's also connected to other works, I mean, maybe you can comment on how you came to looking at this variance constraint problem. I think it's from a very different context.
It's a kinetic theory context. You're talking about the Boltzmann equation.
Yes, maybe you can just say a word about that.
Momentum, which is the mean, and then the variance is the energy.
Right. So
I
I think
2 papers, and there's one. Yeah, but the Boltzmann equation is the short answer.
So I think this idea of having like constraints on the moments, right? I mean, it's very meaningful in physics and many other settings as well. But yeah, the way we came to this was through this sampling problem. And I mean, you want to be able to prove convergence for targets that are non-Gaussian. Because if you have a Gaussian target, then you can just sample from a Gaussian very quickly and efficiently anyways. You don't need to do anything fancy. You don't need to set up a particle system like that or anything, right? But the point is this actually works really well, like empirically, also for non-Gaussian targets. And still we're not able to prove anything beyond the Gaussian case. So that's also an interesting open problem. That, yeah. Okay, so then you have the corresponding gradient flow that gives you an acceleration, right, with a preconditioner here. You get this very nice splitting in shape and moments up to rotations. I still think we can sort of understand a bit better the role of these rotations. Like, for instance, can you write down the optimal rotation? Because you're taking it in for rotations, right? So can you write down what is the optimality condition for the rotation and study those properties and plug them back into the problem and then say something? We haven't done that. Right, we would like to prove existence of geodesics, obviously, without these two assumptions. We get also splitting in entropy and the Fisher information. And yeah, this question of how does this change of convexity properties of the functionals for the covariance-modulated geometry translate into curvature properties of the space? That's something I think that would be very interesting. So yeah, I think I will stop here.